Good evening, everyone. Today we will discuss. Today I built a circuit. It's a half-adder circuit using NAND gates. There is the circuit schematic. I have used 5 NAND gates and to mimic a XOR gate. This 4 NAND gate mimics the nature of the XOR gate, and one NAND gate to mimic the nature of the NOT gate. Ultimately, in total, it works as a half-adder. So for that I have used two HC 74HC00 IC. HC stands for a particular series which has higher clock speed whatever, and 7400 in TTL series it's two input quad NAND gates. I mean, there will be 4 NAND gates, each has two inputs and one output. The 14th pin is connected to the VCC, and seventh pin is connected to the ground pin. Same here with the jumper wire, and the circuit schematic is ditto as same as that, and I have wired such as the schematic, and I have powered the circuit using PD trigger module. This is a PD trigger module. Currently I am fetching 5 volts from the trigger module, and this trigger module got supply the power in this trigger module comes from the my mobile phone charger 68 watts. So let's start the circuit and see. First we will connect both inputs into the zero line, I mean the ground line, which mimics the nature of input as 0. Let's turn on the circuit. The circuit has turned on. The red LED in the trigger module is on. So both let me first show the output. This red LED is the sum. If the LED is on, the sum is 1. If LED is off, the sum is 0. In the blue LED, it's for carry. If the LED is off, carry is 0. If the LED is on, then it means the carry is 1. Okay, off means 0 and on means 1. Red for sum, blue for carry. When the inputs are both 0 0, when inputs are both 0 0, sum and carry both should be 0, and it's 0. Both are off means both are 0. Let's put them in 1 1. It's currently at floating means the voltages are around 2.5 volts, and floating has a very wild nature in the TTL series ICs, and you can see the LEDs blinking without any reason. So let's give 1 1 in the input. I have connected both input terminals. To the 5 volt power supply, mimics both input are 1, and for that the red LED is off but the blue LED is on. I mean the sum is 0. It means actually sum is 0 and carry is 1. So in the truth table also, when the A is 1, the B is 1, then the sum is 0 and the carry is 1, which has been proved by this circuit. So let's put it at 1 0. So the yellow wire here, the yellow wire is the first A input and the orange wire is the second B input. Let's give the input as 1 0. So 1 second. So here I have attached the yellow wire to the 5 volt power supply, means A is 1 currently, and the orange one into the ground power supply means the B is 0, B input is 0. And for that particular scenario where A is 1, B is 0, the sum should be 1 and carry should be 0. Red LED stands for the sum, which is on means the sum is 1. The blue LED, which stands for the carry, is currently off, which means the carry is 0. Same as the truth table. So let's flip the inputs. I mean for now I will put the B input as 1. Sorry, let me attach to it. I mean let me attach the pin to the breadboard, and then the A input to the ground terminal, mimicking the nature of 0. So I have attached the A terminal. So you can see the A terminal, yellow wire is at the ground mimicking 0, orange one which is the B input at the 5 volt supply mimicking 1. So currently it's this A0 B1. For that the sum again should be 1 and the carry should be 0. Again the red LED, which stands for the sum, is on, which represents its 1, and blue LED, which is off, it represents the carry is 0. So I have verified this truth table using my handmade circuit using the 7400 NAND gate ICs to mimic this half adder circuit in the breadboard. Good evening everyone. In this demo, I am going to show the full adder using NAND gates, and here are the three 7400 quad two input NAND gate IC 7400. The schematic is here. As you can see, there are total nine. Sorry, there are total nine NAND gates, as you guys can see, and sorry for the interruption. So there are total 9 NAND gates, as you guys can see, and I have used 3 quad NAND gates to get the 9 NAND gates, and the schematic is same as this diagram. I mean, the connections are same as this diagram, as you guys can see. And there is the truth table, but I don't care about the truth table. Let directly give the demo. And so let's start the demo. First, power on the supply. I have turned on the supply. As you guys can see, there are three slide switches here. This one is A, the first variable. This one is B, the second variable. This one is carry in. For full adder, it's the third variable. The red LED is indicating the sum and blue LED is indicating the carry. So as you guys can see, these slide switches are set to ground right now. So both of three of them are 0. So if three of them are 0, the sum is 0 and carry is 0. Hence the both the LEDs are off. If one of them are 1, then what will happen? If one of them is 1 and rest of them is 0, the sum will be 1 and carry will be 0. It does not matter which variable is the one. If any one of this one and rest of them are 0, then the output is gonna be same. Sum is 1, carry is 0. Let's turn it on. For variable a1 and rest of them 0, it's mimic giving the right output. Okay, my stand is weak, sorry for the interruption again. For b variable 1 and rest of them 0, giving the same desired output as sum 1, carry 0. Okay, good. And let's turn it off. And now for the carry. Now carry is 1 and the both variables are 0. Sum is 1 and carry is 0 at the output. This is the carry in, this is the carry out. So in this case scenario where the carry in is the 1, then the sum is 1 and carry out is 0 because the other variables are 0. The simple binary adding 1 plus 0 plus 0 is always gonna be 1, nothing extra, not any carry. Okay, then all the variables 1 is done. Now let's get the combination of 1 1 and 0. So if I sum 1 1 and 0, the sum will be 0 and the carry will be 1. That's how the binary addition works. So for that thing I have to give the any of two variables, give 1 and one of them will be 0. So first turn a the on, I mean a is 1, b is 1. So when a is 1, b is 1, sum is 0, carry is 1, which is desired. Let's turn b off and give the carry 1. Okay, so for that, where a is 1, carry is 1, the output is also is the desired output. Sum is 0, carry is 1, because 1 plus 0 plus 1 is sum 0, carry 1. Okay, now turn a off and turn b on, and this is also same 0 1 1. So 1 1 is 0, sum 0, carry 1, and there is a variable is 0, so it does not matter. So again sum 0, carry 1. Let's give 3 input 1. If I give the 3 input 1, I mean I add 3 1 3 1 in binary, it should give sum 1, also carry 1. So already the b input is 1, the carry in is also 1. Let's give the a input 1, and after giving, so as you guys can see, both LEDs are on, meaning sum also 1, carry also 1, and that's the actual binary addition. If you add 3 binary ones, you will get sum 1, carry 1. So yeah, I maybe missed one combination of 1 1 and 0, but it does not require. As you guys can see, it's almost, I mean it's actually giving every possible value, and it's actually a fully working full adder. And one more thing to say, that I have used the slide switches instead of manually pulling the wire and putting back down, because there is the problem with the pulling the wire and putting it back down from ground to power and power to ground. The problem was that when the wire was floating in the air, due to that reason, there was a you guys already, those who are from electronics, particularly CMOS, already know the effect of floating points in the digital electronics. So for that reason, the LEDs were blinking very rapidly, and for that is completely undesired thing. We try to avoid that, and it may damage the ICs and the LEDs, of course, because of the undesired and uncalculated. I mean, it's just chaos, complete chaos. And to get rid of that kind of a floating chaos, I have used slide switches, which looks pretty, I guess. So yeah, that's the total practical and turn off the power supply, and yeah, it's all done.